So I know everyone here has probably quite a long day so far with with quite a few lectures. This last lecture is going to be a short but no doubt quite an important one. It's because it's going to be short, it's not going to be as comprehensive as we probably would have liked it, or that you would probably like it to be. But it does provide a lot of food for thought, and it's quite an important one to keep in mind for if you were for any future project in quantum computing. So I'm going to start sharing my screen now. Here. Here. Okay. Uh, okay. So this lecture is going to be on quantum advantage and where we look for quantum advantage. So I think this question of why think about quantum advantage might seem quite stupid. Obviously, we want to think about quantum advantage. Obviously, when we talk about quantum computing, we are always looking for the advantage it might pose. But actually, I noticed when a lot of times when researchers actually start delving into quantum computing algorithms, investigating quantum computing, because it's such a hard topic to wrap your mind around sometimes. They often get lost in the details, and they often, while they are exploring and start experimenting and redesigning their algorithms, there is always this moment of they never stop to there is sometimes never the moment stop. Should we do this, or why, to ask themselves, should we do this? Why should we do this? And what's the advantage if we try to do something like that? So a big part of this lecture is one to tell you what type of quantum advantages that are out there. And two is it's a kind of a call to action to make sure to always keep quantum advantage, or well, at least investigating what quantum advantage might mean for your project at the forefront of your mind, at the forefront of your project, uh, at to at the forefront of your project in order to ensure that your experiments, your project whatsoever, would turn out to be as successful as you hope to be. So why you want to think about quantum advantage is because it's very clearly from the get-go, because it informs you of your metrics for success. It informs you what type of advantage you might want to be looking for. Before you even start thinking about the different types of algorithms that you might want to kind of approach, it helps to identify what is quantifiable, or what, and just as importantly, what isn't quantifiable at any stage of a project or any stage of the algorithm. You need to start thinking about when comparative advantage comes in. And comparative advantage here can be very tricky, because comparative means very different things to different people. To computer scientists or to some quantum computing scientists, as long as you can prove mathematically that there is some sort of advantage with a certain algorithm, that's kind of like, okay, sure, that's all I have to prove. But to those people who are actually implementing it, comparative advantage means something very different. And lastly, in order to make sure that it's always at the forefront of the mind, you need to make sure that it provides a framework that is incorporated into the framework for your project when you think about quantum advantage. When in for a project, so that quantum advantage is always at the forefront, and investigating what type of advantage is there, it's always at the forefront and mind. So with that, there's going to be three parts to the lecture. Firstly, Dikshant is going to give a short lecture on the computational complexity zoo for quantum computing. And in the last 10 minutes of the lecture, the computational complexity zoo is especially important for the different algorithms that we've gone through so far. Shell's algorithms, QPE, Dutch, JOSA. Tomorrow we're going to go through growers as well. This is going to be important for those algorithms. But then we are going to start thinking about other types of advantages of other algorithms where advantage might be a bit trickier to quantify, to think about. Last thing we're also going to think about is about how we can push something to market. And because this is kind of like the big question that many people are asking, when is it going to be useful for industry? And so that's when we need to start thinking about economic advantage. So with that, I'm going to pass over to Dikshant. I can, yeah. I'm going to pass over to Dikshant to go through the computational complexities.
All right. Thanks, Jonas. So in this slide, you can see different complexity classes. All the complexity classes that the major ones that you need to know is in this slide. Some of them you might have seen, some of them you might not have seen. So before we even get into this, let me give like a bit of motivation for why do we need to separate problems into different classes. Well, the first thing is it helps us understand, characterize, and quantify the resource, speed up a problem will require to solve. Sorry, to the solution to a problem will require, right? So and so in this slide, we have both classical and quantum complexity classes. So first, I'll start with the classical ones. Some of them you might have heard before. You might not have heard before. That's fine. And I want this to be not like a one-way lecture, but rather a discussion lecture where I will hope that you will participate as well. So the first complexity class, classical one, is P. So can anyone tell me if they have heard of this complexity class before? P stands for polynomial time. So basically, it's basically classes of algorithm that you can solve in polynomial time. Can anyone give me an example? Any example of algorithm that can be solved with this, solved in polynomial time? There's a lot. Okay. Addition. Okay, addition. Okay, good. What's that? Yeah. Okay. I'm actually not sure what that is. It's the
Pathfinding.
Okay.
It is
Okay. Good. Okay, so let's see what I have. So yeah, as I said, the set of problems that can be solved by a classical computer in polynomial time. The one that I like to think of is one of the problems that you solve as a computer science student, which is given an array, find the maximum element of an array. So that can be deterministically solved in polynomial time. Okay. So the next one is NP. Actually, let me, before I go into the slide, has anyone ever heard of the class NP? If you paid attention to Sebastian's lecture, he mentioned something called NP hard. So can anyone tell me what NP means? Pascal's message here. So non-deterministic polynomial, very good. Okay, so NP means the set of problems that can be verified by a classical computer in polynomial time. So it cannot be solved in polynomial time, but the solution can be verified. Put it differently, it's a set of problems that can be solved with the help of a certificate. And the certificate is essentially a thing that you use to verify. The second one is a little bit confusing. So, and the first one is quite intuitive. So you can just use the first definition. An example of an NP problem would be Boolean satisfiability problems. So this problem occurs a lot in logistics industry. Let's say you have like 10 vehicles that needs to serve, let's say you have 10 fleet of vehicles that needs to serve essentially what you order on Amazon Prime. Let's say you order sunglasses. The sun is in my eye right now. To, let's say, 100 different locations, right? And you're given a constraint because in Amazon Prime, like the delivery needs to happen in like few hours or something if you have the subscription. So there is a time constraint, right? There is number of vehicles constraint, and there is so given these constraints, you essentially need to deliver all the goods in the desired location, so that people can get the goods, right? So that's one example. The other one that Sebastian just mentioned is what is called the max cut problem, right? So finding the maximum cut of a graph. That's another. So that's when he said NP hard. So which means it's if you want to find a global solution to that problem, you can verify it in polynomial time, but you can't solve it, which is why we use QAOA, right? So these two complexity classes in computer science have this famous problem. So before we get into that, can someone tell me what is the relationship between these two complexity classes? In other words, which class contains another one, or which class do you think is subset of another? So basically you have two possible answers. Is P subset of NP, or is NP subset of P? P subset of NP. Why? Why do you think P is subset of NP? And why not the other way around? Chat is saying, okay. So Sharif says, because there is a possibility that the worst case of P is NP. Yeah, that's what I was looking for. So if you think about it, the set of problems that can be solved in polynomial time can also be verified in polynomial. The solution can also be verified in polynomial, right? We already have a solution, right? But if you can verify the solution in polynomial time, that doesn't mean you can solve it in polynomial time, right? So therefore, P is a subset of NP. NP is a bigger class, and then P falls under it. Okay, which is shown by this arrow. So P is a subset of NP. Okay, so another complexity class is Merlin-Arthur. Okay, so before actually, I need to say that these two algorithms are deterministic algorithms, which means that you can deterministically solve or deterministically verify the solution in polynomial time. Okay, but there are algorithms that are probabilistic. Okay, so before I get into that, it's P equals to NP, and this is a year-old question in computer science. It's called the Clay Institute Millennium Prize, and I think there is a $1 million prize for someone who can give a proof whether it's equal or not. It's generally believed to not be equal, but there is no rigorous mathematical proof for that. Just want to mention that. Okay. Yes. Now the next complexity class is actually before MA is BPP. So this stands for bounded polynomial. Bounded probabilistic polynomial class. Okay. So the set of problems that can be solved correctly with a very high probability by a classical computer in polynomial time. Okay, an example of this would be given an integer, determine whether the integer is prime or not. And that would be example of so let's say you come up with a really large number. right? And you want to determine whether that number is prime or not. There are algorithms, probabilistic algorithms that can tell you whether they are prime or not, but they cannot tell you deterministically. Okay, so that's the difference between BPP and P. Okay, and because it is probabilistic, see something in the chat. Make sure. Okay, so that was previous response. All right. So this is the third complexity class, and now we're getting into the probabilistic realm. Okay, from deterministic to probabilistic, and this is actually where a lot of the interesting problems lie, because they are so hard to deterministically solve. We rely on probabilistic algorithms to solve them, just like this criminality system. Okay. Another classical algorithm is the Merlin-Arthur algorithm. And so just like how P is related to NP, which means P can, in case of P, the problems can be solved. In case of NP, they can be verified, right? Similarly, in case of BPP, the problems can be solved. And in case of MA, the solution to the problems can be verified. So MA stands for Merlin-Arthur, where Merlin is the I think there is a verifier, and there's someone who, I forgot the exact terminology, but there's someone who gives the proof or guesses the proof. So Merlin is the person who guesses, and Arthur is the person who verifies. We won't get into the detail of this entire protocol, but it's essentially a protocol that helps you characterize a set of problems that can be verified correctly with a very high probability by a classical computer. And an example of this is something called this graph non-isomorphism problem. And so a little bit about it. So basically, suppose you have two graphs, okay? The question is, does there exist a permutation of vertices of this first graph that is isomorphic to another? Now, this is getting a little bit into the graph theory, but I'm just giving you an example. Okay. The reason why I have an example for every single complexity class is because when I taught this in the quantum bootcamp in Singapore, people asked me for examples, and I didn't really know examples for Merlin-Arthur, so I've added here. All right, so these four all were classical algorithms, and two of which are deterministic, and two of which are probabilistic. Okay. Now, the Q, you probably are looking at the remaining two classes, and the ones that have Q are essentially quantum. Okay, so if I click, essentially you'll probably tell you about the BQP class, but you've already seen it. So can someone make a guess about what BQP class is? Now you can see that this BPP is a direct subset of BQP. BPP, by the way, is bounded polynomial, bounded probabilistic error polynomial. Can someone guess what BQP is? And if you can make a guess, please also give an example. Should be intuitive to follow. You all have already seen examples of this complexity class. Okay, if you can't come up with a definition, make a guess about what problem falls under this class. Anyone? No, no one? All right, so I didn't really get any response. So I'm just gonna tell you the answer. So yeah, BQP is basically quantum version of BPP. Okay, So BPP is where you can solve your problems correctly with high probability with a classical computer. And BQP is where you can solve your problems correctly with high probability with a quantum computer. Okay. And an example of this is finding prime factors using Shor's algorithm. Now, Jonas told you guys during the QPE lecture that while a classical computer can take months to factorize the 512-bit prime number, a big number, find the prime factors of a very big number. So actually, if you go to 2048-bit number, or even half of that, classical computers can take years to find prime factors of such a large number. Will Shor's algorithm really BQP? Some of it is a quantum algorithm, but the rest of it is run on a classical computer. So it is still BQP because of the quantum part, and if you didn't have it, then you wouldn't be able to solve it. It is true that Shor's algorithm relies on partly using a quantum computer and partly using a classical computer. But I think when we say it can be solved by a quantum computer, we also mean that the implicit assumption is also that you're also allowed to use classical computer for some part of it, essentially. So another example of this would be Grover's algorithm. So Grover's algorithm, which you'll learn tomorrow, gives you a quadratic speedup when you're trying to find a marked element in an unsorted database. So basically, in classical case, you take order of n queries, but in quantum case, it's square root of n. It's a really fun algorithm to learn, which you'll do tomorrow.
The Grover's algorithm is quite an interesting case because when we talk about these complexity classes over here, you're normally talking about decision problems. Whereas the Grover's algorithm in unstructured database set is normally a relationship problem. And Grover's algorithm is hard to classify so there are ways to transfer to connect decision problems and relation problems. But it's hard to completely connect Grover's for reasons I'll go through tomorrow. But the short idea is that there are some assumptions we make in Grover that make it hard to put it into a complexity class even after trying to create tenuous relationship between the decision problem and the relation problem. But yeah, so this is also an active area of research in the complexity classes. So this is quite it's quite an interesting space to look at.
Okay, and that's your BQP class. And the last one is QMA. So QMA is this quantum version of MA, the Merlin-Arthur. I hope you can still see my slide. And an example of that would be the local Hamiltonian problem. So essentially, given a Hamiltonian represented by a sum of polyterms acting on qubits, local polyterms, which you'll see tomorrow in the VQE lecture. The task is to determine whether the ground state is beyond or below a certain specified threshold. And that's an example of your QMA. Okay, so all of these complexity classes, especially the classical ones, help us distinguish between the solutions, the list of possible solutions that can exist for a problem. And the quantum version of that it should be quite intuitive to follow because they follow the same definition, but they rely on using a quantum computer. Okay, yeah, so that's all you need to know about complexity classes. And how is this related to quantum advantage? Well, if you can create more list of algorithms that fall on BQP class, and that cannot be efficiently solved by a classical computer, like for example the Shor's algorithm, then you can claim that there is a quantum advantage, right? And so this is why this characterization is really important. So yeah, I'll also say the arrow, by the way, as I said before, they tell you which class is a subset of which class, and there is no rigorous proof for the equality of these classes. So there is no rigorous proof that P is equal to NP, or BPP is equal to MA, or BPP is equal to QMA. But generally, people believe that they are not equal. Okay, so the no comments. So one other thing I need to mention is why would it be important that if P is equal to NP? Let's say sum up with someone like, so why is it such a big deal, right? Why is the mathematical proof such a big deal that they put $1 million prize on it to prove that P is equal to NP? The reason for this is because if P is equal to NP, that would imply that if you can come up with a verifier, or if you can come up with, if you can verify a solution to your problem in polynomial time, then that would mean that it is also possible to solve that problem in polynomial time. Okay, I see a comment. You could find rather than verify solutions. It's actually the other, because the other one is easier. So basically, if you're able to verify a solid solution in polynomial time, then that would also mean that there exists a solution that can be deterministically determined in polynomial time, which is and that would apply for any problem, right? And this is why it's such a big deal. But generally, people believe that it's not true. Okay, for example, for the max card problem, it's not true. I mean, it's not that it's not true, but people if you think about it, you try to find the max cut, all the algorithms that exist out there, including QAOA and classical algorithm, these are all heuristics, by the way, right? So they try to get an approximate solution. There is no guarantee that this is going to be the solution of highest quality or the global solution, but rather you hope that the solution will be approximate enough or of a good enough quality. And it's the same thing applies to, for example, if you open a Google map, right, and try to go from here to let's say I don't know, Rottnest Island, right? Google Map will recommend you a specific route using bus, trains. It's not necessarily optimal, but it's an approximate solution, and it's good enough. Okay. So with this, I will. Okay. Any questions about these complexity classes?
You answered the Shor's algorithm one.
Yeah.
Yeah. So I just to add on, maybe because just to add on to really being P2P is because the order finding part of the Shor's algorithm is actually the hard part, and it's actually going to be the hard part for the classical algorithms as well. Obviously, there's always going to be the question of whether operations on the quantum computer is the same, because you're really counting the number of operations you're performing in the quantum computer as opposed to classical computers. There's always going to be that lingering question mark of, is it really the same if one of them is a quantum operation, the other is a classical operation? But yeah, I think another concern that with Shor's algorithm being in P2P is because these are decision problems, and integer factorization, prime factorization, sometimes it's not phrased as decision problem, but it is possible to kind of like finagle it a little bit to phrase it as a decision problem, which is why it's commonly thought that Shor's algorithm is very well integrated. I hope that answers your question. Oh, Pascal. Yeah.
Okay. Yeah, and this idea of, is it really fair to compare operations on a quantum level to operations on a classical level? Because that's what we did for QFT, right? We said that there is exponential speed up, but the speed up is actually in terms of the number of operations that we do on a quantum level, and we're comparing that to doing operations on a classical level, right? And so we today, for example, doing operations on a quantum level, if the circuit depth is really, really high, it gets very noisy and state gets corrupted and all that. So there is really a question of, is it really an exponential speed up, right? That's up to debate. Okay. One algorithm that like no one will debate for giving exponential speed up is the Dulal algorithm, right? You just need a quantum circuit, and you just run it once, and that's all you need to do, and you find the solution. Okay, I'll hand it over to Jonas.
Okay, so I hope that was an interesting look at complexity classes and what you can think about, and I hope Dikshant has motivated why some people want to think about it a lot quite deeply. It's actually quite it's a very, very active field of research. It's I think one of the most active fields of research within quantum computing there is. And so and it's because it's actually one of the more quantifiable parts of advantage that you can come up with. Just count the number of operations. You can count the number of operations, you can think about it. You can somewhat relate it to the classical complexity classes in some form. There's ways to kind of think of analogs of counterparts to them, and a lot of the quantum algorithms that we have gone through so far follows that Grover's will be the last one, and the Grover's will be the last one that we'll be covering that has such an advantage like that tomorrow. Now, here is actually, this is going to be a sneak peek to what you are going to be listening a bit more of tomorrow. And for those of you who are coming next week, you are going to really have to think about this quite a bit, because this part in the next semester, I'm just going to briefly talk about the other types of advantages that might exist. And unfortunately, these are not going to be as concrete as the complexity classes that that you have just gone through. You've gotten a bit of a first taste of it with the max cut problem that Sebastian just went through. And you're going to cover a bit more of it tomorrow when we go through the Q&As, going through other variational algorithms. And I hope you gain appreciation for how difficult it might be to come out with such advantages. So the first type of advantage that you want to think of is in terms of heuristic. How are you going to come out with advantage for heuristic problems, especially for stuff like the max cut problem that you have already seen just now? We see that it uses the QAA uses is a hybrid classical quantum algorithm, uses a classical optimizer, and it is non-deterministic. It's non-deterministic. Admittedly, for QAOA, if you design it well enough, the longer you run it, the better the result you're going to get. The chances of landing at the optimal point increases if time equals infinity, but obviously that's not the case. Obviously, there's also always the problem of barren plateaus that you might encounter in real life, but theoretically it is possible to get to an optimal point with t equals to go infinity. The problem with heuristics is, well, I mean, because time never really goes to infinity. You are always going to have to think about where the advantage comes in if it's not non-deterministic, because you're not going to have this easily calculable time and operations that you can kind of think of. And the other interesting thing is that you have considered for specific problems. When the first QA paper came out by Fahim, he did it on the max cut problem, and he showed that this is the fastest that people can do it on the max cut problems based on based on the other experiments out there. The claim that he couldn't make is that this algorithm is definitely better than all other classical algorithms out there. In fact, in 2014, was when the Fahy released that paper. Very soon later, people found a classical algorithm that did better than for max cut problem. And he had to do it and this was just specifically for max cut, because implementing QA, you have to redo that advantage analysis every time you change a problem. Related to QAOA is also something called quantum annealing. This is something that you have heard from D-Wave systems. I'll be talking slightly more about D-Wave tomorrow. But this is the classical counterpart to quantum annealing is often simulator annealing. Quantum annealing is also heavily related to QAOA, but it's based on a completely different quantum phenomena, and it's a completely different type of quantum hardware as compared to the gate-based quantum computers that you might encounter. And that's when, how do I really quantify advantage there? You find a lot of these problems in quantum machine learning, particularly for neural networks as well. I would like to invite you to think about how one might argue an advantage for machine learning model, or neural net. Okay, let's be slightly more specific. For neural network model, even just classically, it is extremely difficult to do so. It is extremely difficult to do so classically, and that's why the work of machine learning engineers and machine learning theorists are often have a disconnect. And the problem comes in is that if you can't even really decide the proper way of deciding advantage for machine learning classically, how are you going to argue an advantage for quantum? If you compare one classical machine learning model to another, and you go like, and you don't really, and you have various ways of arguing an advantage, and there is no set way of doing so, how are you going to then add on quantum to it? Here at SoftServe, we had come out with a certain framework in order to argue an advantage for it, and it's usually pretty simple. We'll be going through this in a lot more detail next week for those of you who are attending. But we've classified certain ways that people argue for advantage for different neural network, for different machine learning models in terms of the theory, in terms of experiments, in terms of the design philosophy behind it. Okay. Last, you also have to think about other quantum systems. So, and one of the other quantum systems that I have just talked about was quantum annealing. There are also different quantum hardwares that are not your normal gate-based quantum computers like analog quantum computers. So what are analog quantum computers? Just very simply put, there is kind of like a parallel between analog quantum computers and quantum computers, as there is a computer and an analog computer. So the gate-based quantum computers are more similar to classical computers in terms of like you're thinking of quantum gates as operations. You're kind of trying to form everything tonight into qubits, and then you're thinking everything in terms of operations, and then as it proceeds through, there is a digital quantum computer is often has an extra layer of abstraction added onto an analog quantum computer, which is really about just having a few control over a few parameters in the quantum system, changing it to, for example, fit a certain Hamiltonian and or certain Hamiltonian or certain evolution ways that the quantum system might evolve, and then just letting it evolve and using that for quantum simulations. And there are different ways of arguing advantages for those two that we won't really be going through. Okay, so one example of this is going to be, for example, the many-body interaction modeling. And it's quite difficult to compare this to classical methods, although there are many arguments as for why this would be better. It's simply because it's a quantum computer is able to model a quantum system better than a classical one, but it's quite hard to quantify it at times, and there are many arguments to be made for and against certain ways of quantifying it. The last one that I think I want to just introduce as a bit of food for thought is, I think the industries is to address the industry's interest in quantum computing. A lot of the hype and a lot of the push for quantum computing comes with the assumption that there is going to affect industries one day. This is especially apparent for this is especially apparent when Shaw's came out and says, oh, we can break RSA. Everyone was like, oh, this is a way that this can affect the real world. There's a reason why no one is really that interested in the Dutch algorithm and Dutch Rosa algorithm, because like even though you can prove an advantage there, that's never really going to lead to any real life consequences. So one of the first things that people would think of is, will it make me money? will incorporating this into my systems make me money, or will not incorporating into my system lose me money? I think that's the other question that is probably more relevant for Shaw's algorithm, especially if your cybersecurity is not great, not resistance against Shaw's algorithm, and sometime in the future, that's going to lose you money rather than it going to make you more money. But this is really the core question for So it really comes down to this is really the core question at the forefront of many people's minds. And I think when you are kind of arguing for certain projects in the future, especially in quantum, this is probably not the nicest way to phrase it, but I personally think it's the most realistic way to phrase it, because at the end of the day, it always comes down to the economies of it. There are ways. This is the normal way of pushing things into the market. At this point of the quantum scale, we can really only do research and proof of concepts, simply because a lot of the quantum computers are really not there yet. There are arguments to be made that you can kind of create prototypes for it now. I personally don't really agree with many of those arguments, but yeah, main point is you're never going to get an MVP at this point. So that's at this point of time. But eventually in the future, this is something that you will want to think about. And even early in your project, if you are if you are going to try to make an argument for economic advantage, you are going to want to think about pushing about how your problem relates to the market in the future. So there are several considerations that you need to have. How critical are these services? Would the increase in a certain metric that you're putting up what will it bring to the company? Will it make it money how will it make me money? How long does it take to market? How much to invest in research? What's the financial model? How much does it cost to run the quantum computer? How much money does it cost to book it on AWS bracket? How much money does it take to buy a quantum computer and put it in my own on-prem on-prem service? This is something that these are considerations that maybe you won't have, but many big companies have. No. There are many ways that people are starting to think about this, and this is this is a pretty interesting paper that I still don't know. I'm still deciding whether I agree with or not agree or disagree with. I'm still kind of on the fence about this, but I thought it had a lot of food for thought, and I encourage you all to read up on it. Okay, with that, I'm going to end off this session. I hope this part, the heuristic parts, we are going to go through a bit more of the advantage when we go through certain algorithms about it, and so that you are going to have a bit of a deeper look. I hope you enjoyed the lecture on the computational classes by Dikshant, because that's, I think, the most concrete one that we are going to have. The most concrete quantum advantage conversation that we're going to have for a while. And yeah, and I hope that you enjoyed the lectures today on QFT, QPE, and Sebastian's lecture today.